Morning, guys. So three of you are there.
Morning, sir.
Yeah. One, two, three. Fine. So I think we'll start. Let your friends join. Right. Okay. Right. So we have completed, as I told, we completed all the 11 chapters, right? 11 standard chapters, right? So today we'll continue with organic, right? So we'll try to complete how much ever possible reactions, and then we'll go for some problems, right? Okay. So we have seen all type of say normal reactions will happen in organic chemistry, say electrophilic addition, free radical reactions, what else? Nucleophilic substitutions, electrophilic substitutions, right? And then what? And then Grignard reactions, right? What are the possible reactions with Grignard, right? And then hydrocarbons, almost all things we completed, right? And even I would say your alkyl halides, aryl halides, almost we have completed. We have actually done everything. You don't have to worry about it. We saw benzene mechanism, right? If you remember, right? And then alcohols, we saw alcohols are going to be acidic in nature, right? So because of that, there can be some reactions, right? Even alcohols can undergo nucleophilic substitution, right? So we saw how it will undergo nucleophilic substitution, right? So we know that OH minus or OH is a bad leaving group, right? So we have to convert OH into something else so that it'll be able to go it'll be a good leaving group, right? Say one of the ways of doing this is like this. Say for example, if I have ROH and if I put HCl, right? So I know I'm going to get RCl, but it's not like OH minus replaces Cl minus. Sorry, Cl minus replaces OH minus. It's not like that. So first, what happens is this H plus attacks the lone pair. This attacks the lone pair on oxygen, right? So now you will form ROH2 plus, right? And now the water molecule leaves to form R plus and H2O, right? And then the Cl minus comes and attacks to form RCl. Like this we saw. So this is the way we do it, right? We convert OH into some other thing, which is a good leaving group, that is H2O in this case, right? And then I'll be able to make the nucleophilic interaction happen. Right now, like this, I have one more thing I can do, right? One more what I can do is if I have ROH, right? Now there are something called as tosyl groups, TS. Okay, I'll write it like this. Okay, tosyl, tryphyl, methyl. Okay, so these kind of groups are going to help me make your OH into a good leaving group. Okay, so what do you mean by tosyl, tryphyl? It's tryphyl, right? Tosyl, tryphyl, and methyl groups, right? So the short forms are TS, TR, and MS. Okay, and mostly you will not see these two, tryphyl and methyl. You will not see generally. Okay, but you will see mostly tosyl groups. Say something they'll tell. Okay, what do you mean by tosyl? Tosyl is basically toluene sulfonyl group, right? Toluene sulfonyl group. Same way, tryphyl will be trifluorosulfonyl group. Methyl will be methyl sulfonyl group. Okay, tryphyl is trifluoro sulfonyl, right? Methyl is methyl sulfonyl, right? Okay, so what is a sulfonyl group? Sulfonyl group is very easy. This is what is sulfonyl group. And if I have any other group like R here, and say I can have some other cation. Okay, so this is what is called as your sulfonyl group, right? So if it is going to be toluene sulfonyl, this R would have been toluene, benzene ring with CH3, right? Now if it is going to be tryphyl, I would have had CF3, and this R group would have been CF3. And if it is going to be methyl, then it would have been CH3, right? Okay, so anyways, so now how am I going to convert it? It's very easy, right? So all this is going to happen is because I'm going to have acidic hydrogen in the alcohol, right? This H plus will be able to come out, right? It is little acidic in nature. We already spoke about it, right? Okay. So now, if I write it like this, if I have, I'll write it like something like this: tosyl chloride, right? So you need to have, yeah, tosyl chloride. If I have, right? So now what is going to happen is this H plus and this Cl minus will go out because this is acidic in nature, right? So what do you have here is ROTS. Now this sulfonyl group will attach to the oxygen. Okay, this sulfonyl group will attach to this oxygen, and I will have H plus and Cl minus removed to become HCl. Then you can do any nucleophilic substitution. Okay, because this is a very good leaving group. OTS group is a very, very good leaving. Okay, right, fine. So this is the first way of doing it. Like generally they don't undergo any nucleophilic substitution, right? But I can have nucleophilic substitution if I can convert it into a good leaving group. That is the first time. I mean, that is the first way. This is the second way using any of these three groups: tosyl chloride or anything. It can be any anion, doesn't matter. Okay, so tosyl, I'll get H plus removed, I'll get ROTS, and this can undergo any nucleophilic substitution, right? So I can put anything, I can put so many nucleophiles, I can put Cn minus, anything is fine. It is going to undergo nucleophilic substitution, right? Fine. Now in alcohols only, right, we have another kind of nucleophilic substitution. I'll tell you what is it. It's not. Okay, it's not alcohol, it's actually an alkyl halides. So the name, I'm going to see. Williamson synthesis, right? So this will be in your alkyl halides chapter, correct? So hope you remember the reaction. Remember, the reaction goes like this: Rx or any RCl or whatever it is. If I put RO minus Na plus, so we write it like this generally. We write it like RONA in the presence of ROH. That's how we write it, right? So R, or maybe if I can put R dash because I already have an R, right? Now we know what is going to happen. Basically, the RO minus is going to replace the X minus, correct? So I'll be ending up with your ethers, RO R dash, right? So this is a simple nucleophilic substitution only, right? But what you have to understand is, based on what is the alkyl group present here, right? Generally, I will have, no, there is not much of a deal here. I don't think so, right? One second, just give me a moment. Okay. So the thing is, here the R which I have here should be primary. Okay, should be primary. Right, now why is it like this? Right, now you can easily understand this can act as a base also. Right, RO minus is a good base. Right, so when I have base, say for example if I had alcoholic KOH, right, alcoholic KOH, what happened? I had elimination reactions happening. Correct, say for example if I had CH3 CH2 Cl, and if I go for alcoholic KOH, means KOH in the presence of ROH. Right, so what will happen? You will be getting CH2 double bond CH2. Correct, now the same reaction, now I told you, like instead of this I can even use this RO minus Na plus in the presence of ROH, that also can act as a base. Right, so now in this case you see there is a nucleophilic substitution reaction happening. Right, okay, so but if this R is secondary or tertiary, I will be getting elimination product, in the sense that I'm going to form alkene. Right, only case where I can get ethers formed if this alkyl group R, if it's primary. Right, I don't know, I don't care about this R group, that doesn't matter. Okay, but this R which is coming here from the alkyl halide should be primary. That's the point. Okay, so that is about. Sir, yeah,
so this is SN2 mechanism.
Yes, this is definitely SN2. Definitely SN2, because there is no way that I can form carbocation here. Remember, this is going to be SN2, right? And there is no way that I'm going to form any carbocation here. No, it's not possible. Right? Good question. Yes. Right. And then that's about Williamson synthesis. And then we will see a little bit more about ethers. Okay, guys, I'm not going in any structured way. Okay, so generally I will be going in a structured way, because now that I've already completed most of the reactions, whatever I have not completed, that's what I'm concentrating on. Okay, fine. So right, there are other ways of producing what is that, your ethers. That would be when you have, say, a C double bond C. Right, you can go for electrophilic addition of an alcohol. Okay, you can go for, am I right? Yeah, right, I'll be able to go for an electrophilic addition of alcohols. Right, so what will happen? Obviously I have RO minus H plus. Right, it's an electrophilic addition reaction, so obviously the H plus attacks. Right, and then I form the carbocation. Then what is remaining is your anion with the carbocation. So this RO minus will attack the carbocation. Very easy. All the same electrophilic addition. In this case, I'm going to have ROH. Right. So now you'll see that I'm going to have, say, CH comes here, H plus comes here, and you can see that OR goes here. Okay, so you can see this is an ether. COC bond will be there. So that will become an ether. Not only this, people, I can even put anything. I can put RCOOH, like I'll have H plus and RCO minus getting attacked. I can even put RX, R minus X plus, sorry, X minus R plus will attack. So everything is possible. If I have an alkene, all type of addition reactions are possible like this. I think we even did one question when I had RCOOH. Correct? Okay. So those are the different methods of preparation of ethers, right? Okay. Now there is only one reaction for ethers. Okay, and that I'll tell you, right? What is that? Right. I hope there are no questions. Right. So that if I have ROR dash, right? Now you must have seen this reaction, HI, right? Okay, so now you know what is going to happen. So basically I am going to break any one of the bond. I'm going to break one of the CO bond, either this CO bond or this CO bond. Say for example, if I break this CO bond, right? Now it's easy for us to understand. Like you will see that H will come here, I will come here, right? So you will see I'm going to get RH plus R dash I. Right, now please understand, if this was in excess, this product wouldn't have been formed, because this also will react with HI, to form Ri. Okay. Now, if they give equivalent amounts, if they give the stoichiometric amount required for Hi, then you will end up with this product, these two products. If this is going to be given in excess, this also will be converted to the iodide. Okay. Now, the question is, which alkyl group will get the alcohol? Which alkyl group will form the iodide? That's the question now. Correct. Right. Now, okay. Now you have to understand the mechanism of how this is going to happen. Right. Now let me look into it. If I have ROR dash, first the H plus comes, it is going to attack the oxygen cis lone pair. So what will you have? You will have R O. The oxygen will have a positive charge, and this will be done. Then what is going to happen? Then I'm going to have nucleophilic substitution. First is addition of H plus, then the nucleophilic substitution of I minus. Welcome. Right now, this will, it's like, say, either this will be a good leaving group, like this R dash OH plus will be a leaving group, or say ROH will be a leaving group. So either way, right? So now you will have nucleophilic substitution happening. So you'll have RH plus R dash I. This is this you can consider as SN1 or SN2. Okay, that depends on the alkyl group which is going to treat. Right. So I'll tell you some things regarding this. Okay, just give me a moment. Right. So if both alkyl groups, if both R's are primary, right? If both R's are primary, so now I told you this can be SN1 or SN2. Okay, if both are primary, I mean, if this reaction can happen either via SN1 or SN2, right? And if you find that both these R's, say R and R dash, right? If both these R's are going to be primary alkyl groups, right? Please understand the smaller R gets the iodide. Remember like this. Obviously, right? Now you understand if both are primary, right? And as obviously, if primary is there, I'm going to have SN2 mechanism happening because they are more reactive towards SN2, right? Now, in that case, what will happen? The I minus will try to attack the less sterically hindered alkyl group. Is it not? Right? If it is SN1, if it is SN2, right? If both are primary, obviously I'm going to have SN2, undergo SN2. So obviously the I minus will try to attack the less sterically hindered alkyl group, and that only will form the iodide. For example, if you had CH3O C2H5, right? Now if I go for HI, right? Now you see both are primary, right? So the smaller alkyl group gets the iodide, and the bigger alkyl group gets the alcohol. Okay, right. Now, if one of them is primary and other one is secondary, or say one of them is primary, other one is tertiary, right? Now, in that case, just let me 1 second. Let me tell you that. I obviously the tertiary should get the halide. Correct. Right. So when I have one of them to be primary or second, one of them to be tertiary or secondary, Okay, so if I have one of them, if one of the R's is secondary or tertiary, right? The R which is secondary or tertiary gets the iodide, right? The R which is secondary or primary, secondary or tertiary gets the iodide, because in this case, SN1 reaction will happen. Carbocation formation is going to happen. For example, if you would have had CH3, O, CH, CH3, CH3, something like this, and if you would have gone for HI, right? Now understand that the tertiary or this one is going to get the iodide. For example, I would have got CH3, CHI, CH3 plus CH3OH. Now the smaller one forms the alcohol, right? And the tertiary one forms the, sorry, secondary or tertiary will form the iodide, because in this case it's going to be in terms of SN1. Okay, right. Now there'll be a small deviation from this if one of the alkyl groups are going to be aryl group. For example, right, say if I had CH3O, or let me write it like this, OCH3, if I had, and I go for HI. Right now, in this case, please understand, guys, this cannot cleave. This bond cannot cleave. Impossible. Because I know it's an sp2 hybridized carbon. sp2 hybridized carbon with oxygen bond is a little stronger. Obviously I'm going to have double bond character because of resonance. Correct. So this bond cannot cleave. So as soon as you see one of the alkyl groups is going to be an aryl group or a benzene group, right, blindly put alcohol there, right? Because this bond cannot break. The only way you can break this, put H here and I here. So you'll always end up with phenol and CH3I will come. So there are three cases. Okay. First case, when you have both the alkyl groups to be primary, and in that case, it is going to undergo SN2 mechanism. The smaller alkyl group gets the halide, right? Second case, if one of them is primary and other one is going to be secondary or tertiary, then it is going to follow SN1 mechanism. So the secondary or tertiary halide will form, secondary or tertiary alkyl group will get the halide. And lastly, if one of the alkyl group is tertiary, sorry, one of the alkyl group is an aryl group, the aryl will get the OH. Phenol will always be a product, because you will not be able to break that bond. CO bond in benzene ring and O bond, that you will not be able to break. Okay, so these three are the cases. Right, fine. So that is about the cleavage using HI, or you can actually use anything here, HI or HBr or HCl. You'll be able to use anything, right? Okay, fine. Now, next thing, I'm going to introduce you to another kind of a functional group, right? That is also important. Right. So I'm going to introduce you to something called as epoxides. Okay. Now, epoxides are like a kind of ether, right? But there will be a small difference. This is the structure of epoxides. I am going to have one CC bond. Here also, I'm going to have a COC bond, but the oxygen atom is not in between two carbon atoms. It is going to look like this. This is what is an epoxide. Okay, I have a CC bond, but I have a cyclic structure present. Not like oxygen atom is in between the carbon atoms. That will become a proper ether. If you're going to have a structure like this, these are what are called as epoxides. For example, say I can have CH3. Let me read it like this. Okay, CH3, 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 something like this. This is an epoxide. Okay, now the question is, how do I, there are only two reactions I'm going to tell you regarding this. One, how to prepare them. Two, what are the one reaction is only possible. I'll tell you what is the reaction possible. Okay, right, fine. So we'll see what is going to happen. Right, now how do you prepare epoxides? Right, you can easily prepare epoxides when you have a C double bond C, right, and you are going to put something called as an peroxy acid. Did I tell you this reaction before? Because I remember talking about peroxy acids. In which case we spoke about peroxy acids, people? Did I tell you this reaction before?
Yes, sir.
Okay, I told. Anyways, we'll see it again. Not a big deal. So peroxy acid, I told you how is it going to look. Right? This is what is a peroxy acid. Right? Now you will have this oxygen coming here and it is going to go and you will be forming the epoxide. Very simple. Right? Now I told you there is a famous peroxy acid and that only will come in the question. What was that? There is a famous peroxy acid, right? There is there's some collection of words. Do you remember?
No, sir.
Okay, so that is MCPBA. Okay, so meta chloro peroxy benzoic acid. Okay, so they'll either give like this or they'll just give MCPBA. So you have to know that it's a peroxy acid and I'm going to form a epoxide. Okay, right, cool. So next thing is, what are the reactions possible? Right, now if I can actually, I'll be able to cleave that epoxide bond and I'll be able to introduce another nucleophile in the picture. Okay, now say if I had, right, say now I'll be able to do this particular reaction in terms of in two ways. One is acid catalyzed, right? Another would be base catalyzed, right? Or say there is no acidic medium without acidic medium, something like that, right? Okay, for example, if I have say H plus coming first, okay, first H plus coming, right? Now this H plus obviously will attack the lone pair on this oxygen, right? Now what will happen? I will have OH plus. Okay, now what will happen is I will have a nucleophile coming, right? Now this nucleophile can either attack this carbon or this carbon, right? Now you don't have any suggestion. I'll tell you which carbon it will attack, but for now to understand the mechanism, now say if this attacks this carbon, this bond will break, right? So what will you end up with? You will end up with OH. Obviously there is a H plus along with this, okay, and you will see there is another nucleophile which attacked this carbon, and I'm going to have a structure like this. Okay, now this is acid catalyst because you use an acid H plus, right? Now I can even have it as base catalyzed in the sense I can directly put the nucleophile, right? Say this is first. Second way, right? Now I can directly put a nucleophile, right? Now what will happen? Say if this attacks this one, the oxygen will get the negative charge. So you will see that I'm going to have O minus, and I have the nucleophile here. And obviously, if I go for hydrolysis of this will form OH, and this will form nucleophile directly. Okay, right. Now, why is there, even though I'm going to get the same product, you see alcohol and the nucleophile is going to get attached, right? But based on what mechanism I'm going to follow, the nucleophile attacks which carbon will be different. Okay, now please understand this particular case, first case, is like SN1, not exactly SN1, but like SN1, right? Now in this particular thing, you can assume that it is going to be like SN2. Okay, now if you can remember this, because you can easily see if that breaks at some very small small portion of time where this carbon where the nucleophile is attacking is going to have some kind of nucleophile, I mean some kind of carbocation, but not exactly that. Okay, so please, anyways, you can understand that it is like SN1, this is like SN2. Okay, Now, if you can understand this, you'll be able to easily answer the question. Right now, please understand, if this is going to be this one, like this way, like SN1 mechanism, the nucleophile attacks the bigger or more substituted carbon. Right? Say out of these two, whichever is more substituted, obviously I'm going to have more stable carbocation in that case. Correct? So out of these two carbon, whichever is more substituted, that one will get the nucleophile. Right? Now here, it is little like SN2 because the things are happening simultaneously. Right? So here, the nucleophile attacks the less substituted carbon. So out of these two, whichever is less substituted, that carbon atom will get the nucleophile. Okay, maybe if I tell you in the form of an example, you'll easily understand, right? So if you have taken this down, I can rub this part. Okay, all right. Say I should give you a proper example. Okay, good example. Fine. Say I had this is CH3, this is CH3, this is CH3, and this is H, assuming. Right. Say now, if I put water, water will not be a good example. Say I'll put HCl. Okay, now this is definitely acid catalyst. So this is going to happen like SN1. Correct? Right. Now you understand the nucleophile here is Cl minus. What did I tell you? The nucleophile should attach itself to the carbon atom which is more substituted. Correct. So out of these two carbon, obviously I understand that this carbon atom is more substituted because it is having two methyl groups. This carbon atom is having one methyl group and one hydrogen. So definitely this is more substituted. Right. So you will see in the product that so if I write it properly, so I start with this CH3. Now this carbon would have gotten the nucleophile, that is Cl minus, and there is another CH3. Okay, and this carbon would have got the alcohol. Now COH, and there is CH, CH3. This H and CH3. This would have been the product. Okay, I told you more substitute. If it's going to be acid catalyzed, more substituted carbon atom will get the nucleophile. As simple as that. Right. Now, for example, if I have done something like RMGX, okay, this is a Grignard reagent. Correct. Now there is no acid present in this. Right. Now, what did I tell you in this case? It is going to react as if it is going to undergo SN2 mechanism. Now, in this case, the R minus, which is the nucleophile, will attack the carbon atom which is less substituted. Right? Say what will happen then? You will see that CH3C. Now this carbon will get the alcohol, right? So COH, CH3. Now the lesser substituted one is this. Say I would have had CH, CH3, and this would have gotten the R. Right? So hope you understood the difference here. Right? If it's acid catalyzed, more substituted carbon will get the nucleophile. If it is base catalyzed, or if there is no acid, then you will see that I'm going to have the nucleophile attacking the less substituted carbon. That's it. As simple as that. Very, very simple. Okay, fine. So that's about your. Obviously, I have to go for hydrolysis. This after I put this thing, because you will have ROMGX present, and then you have to go for hydrolysis to form ROH. That is understood. That is self-understood, self-explanatory. Okay, right. And one more, please understand. These epoxides are also called as oxiranes. There is another name, right? Epoxides are also called as oxiranes. Okay, so yeah, that's about your ethers and epoxides. Okay. So anything else left in alcohol, ethers, alcohols chapter and ethers chapter? Oh yeah, and the other thing would be in alcohols, test for primary, secondary, and tertiary. Right. So test for primary, secondary, and tertiary. Can you tell me what is the test called as? Alcohols. Do you know any test?
Lucas test.
Lucas test. Correct. Lucas test. Right. So I go for anhydrous ZnCl2 in the presence of HCl. Correct. I mean HCl in the presence of anhydrous ZnCl2. Right. So I think I don't have to write the reaction here. If I put that, basically that is a nucleophilic substitution. Right. Alcohols getting converted to alkyl halides, alkyl chlorides in specific. Right. So in that case, you have to understand that it is going to undergo SN1 mechanism. Right. So obviously tertiary alcohols will react fastest and primary alcohols will react the slowest. Right. And as I told you that alkyl halides are going to be insoluble in water. They're going to form turbid solutions. Right. So in case of tertiary alcohols, the turbidity is formed right after you add the HCl in the presence of this thing, ZnCl2. And secondary, it is going to take some 5 to 10 minutes. Right. And in primary, it will happen only after the turbidity will occur only after heating, because the reaction is pretty slow. Right. So that is about your test for primary, secondary, and tertiary alcohols. Right. And there is one more thing, guys, in alcohol, very important reaction, and you will see that even happening in case of what is that? Your aldehydes and ketones as well. Right. So let me tell you that. Right. So you have something called as an iodoform reaction. This I think would have been there in your NCRT also. Okay, iodoform reaction. Right. Fine. So please understand, people, this will be possible in case of alcohols, right, and aldehydes or ketones. Right. Now you can ask me, sir, how is it like this? Now, if in the first step, basically, whatever the reagent I'm going to put, okay, now that reagent is actually going to be a little oxidizing agent. Okay, so if at all there are alcohols, those alcohols will eventually get converted to aldehydes or ketones depending on what kind of alcohols I have. Primary alcohols, aldehydes; secondary alcohols, ketones. And then actual reaction is given by only aldehydes or ketones. Please understand that. Okay, actual reaction is given by aldehydes or ketones only. Okay, so let me see what is happening here. Right. Okay. Fine. So now there is a condition. Actually, we will take the reaction with respect to aldehydes or ketones, and then I'll tell you. Easy, right? Then you have to understand that there's one more step which was prior to that. That would have been oxidation. Okay, fine. Now, what you have to understand is, people, for aldehydes and ketones to give this iodoform reaction, I should have an alpha methyl group. Very, very important. Okay, so if at all I need to have this aldehydes and ketones to give the iodoform reaction, right, you have to understand that they should have an alpha methyl group. Right. Now, this is a very big mechanism. I have to at least clear the board 3 times for you to explain the mechanism. So I am not going to explain your mechanism. If you're interested, go check the internet, and or you can just read any textbooks if you have. If they have the mechanism, well and good. Or else you don't need to know the mechanism. Forget about it. Nobody is going to ask you, and you really don't have to remember it like that. Okay, fine. Now, what is the reaction? Now, let me take a specific example. I have, say, CH3, CO, CH3. Now, please understand, they are telling in the alpha position, not a hydrogen, not any other thing. I should have a methyl group. CH3 should be there. Only then this reaction is possible. Right. So this is the main carbon atom. Right. Now, these two are my alpha carbon atoms. Now, when you see that in the alpha position, I have methyl groups present. So this will give iodoform reaction. Right. Now, you have to add NaOI. This is my sodium hypoiodide. Right. Sodium hypoiodide. Right. Now, this sodium hypoiodide is going to be unstable. So it is prepared in situ. Hope you know what is in situ. Can anyone tell me what is in situ, people? What is in situ? In situ preparation. What do you mean by that? Okay. So in situ means this cannot be stored because it is unstable. Right. So this will be prepared as and when required. You'll directly put the reagents required for you to prepare this directly in the reaction medium. Okay. Then it will be produced and that will undergo the reaction. That is what you mean by in situ. Wherever required, you prepare it and directly use it in the reaction. Right. Now, how will you prepare it? So they will either give it like this, NaOI, or they will give it like this, NaOH in the presence of iodine. Okay, NaOH in the presence of iodine will form sodium hypoiodide. This is how you prepare it in situ. Okay, so NaOH in the presence of I2. Now, what are you going to form? Is very simple. Now I told you it's all about the alpha methyl groups. So one of the alpha methyl groups are going to form iodoform. Okay, and please understand this will be an yellow colored solution. Sometimes it will be even precipitated. Okay, this will be yellow in color. Iodoform will be in yellow in color. So I can even go for any other halide. I can go for bromine, I can go for chlorine, but this color will not be formed. That's why we are specifically going for iodine, right? So like these are the, say for like, why are these things used if you ask me, right? So if I have an unknown organic substance with me, right? Now there are various ways by which we'll be able to test what is the functional group, what is the structure of the functional group, right? So now these kind of small things are going to help. Oh, okay, fine. If this undergoes, definitely it would have been an alcohol or it would have been an aldehyde or ketone with an alpha methyl group. So you'll be able to assign some details you'll be able to get regarding the structure of the molecule. Okay, so anyways, now one of the alkyl group is going to form CHI. Right. Now, obviously, there is something left after this also. Correct. Now that will form C. Now you see there is a CH3. Right. Now this is going to get oxidized. Right. You are going to form COO Na. CO minus Na plus. Okay. Right. So one of them will form the iodoform. Right. The other will form the salt of the acid. Whatever is remaining, just make it into a salt of an acid. Okay, now if I have to give you one more example, say I had CH3, CHO, for example, I had. Right, now again, this is the main carbon atom. In the alpha position, I have a, what is that? Alpha methyl group. Right, so again, if I'm going to put your NaOI or NaOH in the presence of I2, this will form CHI3. Right, this will be yellow in color, right? And this is going to form the acid. Can you tell me what acid is going to form? What will be the acid?
Formic acid.
That formic acid, HCOO minus Na plus. That would have been the acid form. Okay, right. Now, if you do not have, say, now we started with alcohols, right? So let me take an alcohol maybe and explain you. Right. Say if I would have had something like this. Okay. Now this is the carbon atom containing the functional group. So you see this would have been the alpha carbon, this would have been the alpha carbon. Right. But this cannot give me iodoform because this is not alpha methyl group. But this can give me because it is going to have an alpha methyl group. Okay. Right. So now if I put NaOI, right, now this entire thing will form CHI3, right, and this entire thing will form acid. So it will form CH3 plus CH3, CH2, CH2 will not come, CH3, CH2. Now this has oxygen, so you'll form COO N. Okay. Now there is one step which was missing. The first step would have been converting this into a ketone because this is a secondary halide. Right, now ketone would have been formed, and then whatever I told you will happen exactly the same. Okay, right. Now, if I ask you whether this will undergo iodoform reaction, if I put NaOI, will you get iodoform?
No, sir.
No, because this is not a methyl group. This is not a methyl group. You might have some reaction happening. Okay, and you don't have to worry about it. Okay, you might have some reaction happening, but you are definitely not going to see any yellow color for sure. Okay, fine. So that is about your very important reaction, iodoform. Right? Okay, and the reason if this happens is again because of acidic alpha hydrogens present. Right? So all the thing is acidic alpha hydrogen, if I have one of them, if I have so many reactions are possible, but if I have 3 acidic alpha hydrogens, only then this reaction is possible. 3 acidic alpha hydrogen means obviously that's what I'm telling, like alpha methyl group. Okay, and all these things will be converted to iodine, right? And you will be able to form the iodoform, yellow color will be formed. Right. Okay, so that's about this thing. Okay, there is actually some more reactions with alcohols. Let me tell you that. Okay, so we are going to see this reaction. I don't know whether you have heard it. I'm going for pinacol, pinacolone rearrangement. Okay, pinacol, pinacolone rearrangement. 1 second, I will get to you to that. Yeah, okay. Right. So for pinacol, this will be given only by vicinal diodes. Right. This will be given only by vicinal diodes. Basically, 2 adjacent carbon atoms should have OH. Right. Only then this is possible. Right. Okay. So let me directly now maybe. If I had to. 1 second. Okay, so if I have to give you an example, I will have, say, for example, CH3COH, CH3OH, CH3. Now, nothing I have to do. I just have to put a H plus. Nothing else I have to do. Okay, and obviously I have to go for heating. Okay, H plus and heating. What will you end up with? Is like this. CH. What is this? Okay. CH3, 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 C double bond O, CH3. This plus H2. Right now, this is what you would have end up. Okay. Now, this is what is called as pinacol. This will rearrange to form pinacolone. This one is what is called as your pinacolone. Okay, right. Now, like, do not mug up anything, right? Go by the mechanism. For these kind of reactions, you should go only by the mechanism, or else you'll end up somewhere wrong. Okay, so we will look into the mechanism of this. Like questions might come. We don't know. Organic, we can definitely not say which area questions might come, so it's better to know everything, right? Okay, so if I had to go for the mechanism, please take this down first. I'll let you know the mechanism. Okay, I hope you've taken it down. Right. Say now, let me take a normal case. Okay, right. Say first, I add H plus to this. Right. Now there is no, now it's a symmetric alcohol, so I don't know where it is going to attack. Let me take a random thing. Say I have a lone pair here. Now it is going to come and attack. Right. Okay. Now what is going to happen is this is R, this is OH, R, OH2 plus, then this. Okay, right. Then what is going to happen is obviously I'm going to remove this H2O. So what will you have? C R O H R, sorry, C R R with the carbocation. No issues. Okay, right. Now what you're going to see is, guys, you are going to have a rearrangement, carbocation rearrangement. Okay, so carbocation rearrangement means this is already, you can ask me, sir, why rearrangement is going to happen is because I am going to have a more stable product formed at the end. Okay, see, please understand, C single bond O compared to C double bond O, C double bond O is stronger. You can look at the product. If you just look at the product, what I had there, I had a ketone form, right? So that only drives the product towards the rearrangement. I mean, that only drives the reaction towards the rearrangement. Okay, so anyways, now I'm going to have a rearrangement happen. Right, now how rearrangement will happen? You have a lone pair on oxygen. Okay, now that lone pair will come here, make a double bond. Right, now one of the alkyl groups is going to go attack the carbocation. Again, I repeat. Right, so now okay, fine. So this should have easily understood. H plus attacking, water molecule removed to form a carbocation. That's the first step. Right. Next, what is going to happen? You have another OH group which is having a lone pair. Now that is going to go make a double bond, and obviously this carbon atom is going to have this carbon atom cannot have 5 bonds. So obviously one of the alkyl group migrates to the carbocation position. Right. Now what will happen? You'll see that you have R, C, double bond O, H plus, because this has lost a lone pair. Right, now what is there? I have C, R, R, and R. Right, and obviously what I have to do, I have to, from this minus H plus, I have to remove this H plus to form R, C, double bond O, C, R, R, and an R. Okay, just compare it with the product which you saw. All of them were CH3s in the example I gave you. So one of the CH3s would have migrated. Okay, so this is what is called as phenolone rearrangement. Very, very easy. First step, addition of H plus to any of the alcohols. Right, I'll tell you which to do. Don't worry, this is symmetric case. And then you remove the water molecule, form the carbocation, and then undergo rearrangement. Rearrangement which should start from the oxygen's lone pair. That will go make the double bond, then the R will go attack the carbocation. Now everything is done. Remove the H plus at last to form the ketone. That's it. Okay, now I am going to give you what if I have unsymmetrical case, right? That I'll tell you. So what you have to understand is, first thing is you are going to form a carbocation. Correct. So obviously the first step would have been to understand that more stable carbocation should be formed. Correct. Right. So if at all I have to give you some examples, then you'll maybe understand. Okay, first step is the carbocation. So obviously I have to make sure that a more stable carbocation is formed. You know how to decide the stabilities, right? Okay. Now next step is, if I found the most stable carbocation, right? Say now assume that this was the more stable carbocation. Assuming, I don't know, right? This was the more stable carbocation, depending on what kind of alkyl groups you have, right? Now the next question is, I have two alkyl groups. If two alkyl groups are same, no problem. Now next thing is, if they are different alkyl groups, if I have here, which will undergo rearrangement? Which alkyl group will undergo rearrangement is the next question. Okay, so we'll try to answer all those questions. Okay, now first thing what I'll give you is the migratory power. Migratory power means if I have different alkyl groups, different species, which will migrate? Which will, like say you saw that this R was migrating, right? Now what are the, like if at all I have two different R groups, which will migrate with respect, like which will, like I mean, which will migrate over the other thing, right? Okay, that I'll tell you now. Hope you have taken down the mechanism, guys. Okay, so I'm talking about the migratory power of different groups, right? Say migratory power. First, understand H has the maximum migratory power. Okay, then comes phenyl group, right? Then comes tertiary. If at all you have any tertiary.
Sir, I actually have a doubt in the previous mechanism.
Yeah, tell me.
Sir, like after the methyl shift, sir, like there will be a
Alkyl shift.
positive charge on the carbon, no, sir. Like after.
Okay. See, that positive charge will be gone, right? How positive will be gone? Same. Now you had OH, R. I had a carbocation, R and an R. Right. Now, how will there be carbon? Now, see how the rearrangement happens. It starts from the lone pair on oxygen. It's not like randomly this rotates and I'm going to form a carbocation here. No. Right. If this just goes, yes, I'll have a carbocation, positive charge on the carbon. But you see, you broke a bond and you are making a bond here. Understood, Varun?
Yes, sir.
Right. You are. It's not like you are only breaking a bond. You are making a bond and then breaking the bond. So it is satisfied. There is no positive charge.
Oh, okay.
Okay. Right. Right. So I have tertiary alkyl groups. Then maybe secondary. Then maybe smaller alkyl group CH3, CH2, and the least capacity is for CH3. Right. So this you have to remember, people. There is now there are so many. There is not one reason behind this. Say one of the reason would be to say the smaller one. Say if you ask her why hydrogen here, because that is very easy, right? It is very small, which will be able to easily migrate. Right. Now, second thing would be to stabilize the carbocation form. See, you have already a carbocation formed in the first step. Right. Now you have to stabilize a carbocation. So obviously phenyl groups, tertiary groups, secondary groups will be able to stabilize the carbocation a little bit more if it migrates. Right. So there are two reasons here. One, like I forget about hydrogen. Hydrogen for alone, there's a separate comment. The thing is, it is because it's very small, it's very fast, and then it will go and attack. But all the other things you can understand. Other things you know that these things are because of ability to stabilize the carbocation. Right, ability to stabilize the carbocation. Okay, right. Now next thing is, if I have an unsymmetrical case, which will form the carbocation? This is after forming the carbocation. I'm talking about the migration, the rearrangement. Right. Now the first question would be, which will form the carbocation first is the question. Right. So now that to answer that question, you have to easily understand that a carbocation which is more stable, that only will be formed. Okay, for example, if I would have had PHC OH, say PH, say another PH CH3 OH. Okay, I have this particular component. This is unsymmetrical case. This has two pH. This has two phenyl groups. This has one phenyl group and one methyl. Right. Okay. Now, if I put H plus, right? If I put H plus, now you have to understand that obviously the more stable carbocation should be formed. So please understand, either this carbon or this carbon can have the positive charge, right? Now tell me, if I put the carbon number 1 and carbon number 2, which will form a more stable carbocation? Both are tertiary only, right? But tell me which will form more stable carbocation.
Second one.
Okay, one vote for goes for 2. Anybody wants to accept or contradict to this?
Sir, I couldn't hear you.
What I'm asking is, these two carbocations are capable of forming the carbocation. Basically, it depends on H plus attacks which of the OH groups, obviously, right? Now I'm asking, say, assume that these OH groups are not there, right? Which, if I have a positive charge here, that will be more stable, or if I have a positive charge here, that will be more stable.
1, sir.
Okay, one vote goes for 1, one vote goes for 2. Any tiebreakers? Now I'm like, depending on the tiebreaker, I'm going to believe that democracy is good or bad. So do it carefully. I just want one more guy. Go for it. Oh, I don't know how many people are.
Sir, you asked whether 1 is more stable or 2. Like when...
No. That's not a. Don't confuse yourself. If this OH group leaves, I will have carbocation here. If this OH group leaves, I will have a carbocation here. Which will happen? That will happen based on which is a more stable carbocation. I'm asking. Right. So you will have 1 or 2 will form the carbocation. Which one? Still looking for a tiebreaker. Tiebreaker. Is there anything?
Sir, I think 1 will form the carbocation.
1 will form. Okay. Now I believe in democracy. Okay, so it's correct. Right. Fine. So the thing is, guys, right? Let me tell you. Fine. So look at this. I have pH, and say if I have a carbocation here, and then this would be, say, the other. Okay, fine. Say C, pH, and CH3. OH, obviously. The other case would be pH, OH, C, pH, CH3, a carbocation. Correct. Now, please understand, this phenyl group will stabilize the carbocation by resonance. Correct. Right. Now, alkyl groups in general will stabilize the carbocation by or inductive effect or
resonance.
No, resonance will happen only if I have benzene rings, phenyl groups.
Hyperconjugation.
Absolutely true. Right. So either alkyl groups, if I have, they will stabilize the carbocation either by inductive effect or by hyperconjugation. And both of them are not so important when it comes to resonance. Please understand, resonance should be given the first priority. Second, hyperconjugation. Least priority is given for inductive effect. Okay, so you understand here, there in this case, there are 2 phenyl groups that are going to stabilize the carbocation by resonance. Right. In this case, I have only 1 phenyl group is going to stabilize by resonance. The other one is going to stabilize by, so in this case, stabilized by hyperconjugation, which is not so stable compared to the other one. Right. That is why what we say generally, when you have tertiary phenyl groups, carbocation, I'm talking about carbocation, tertiary phenyl carbocation is more stable than a secondary phenyl, right? So after everything only normal tertiary comes. So many things will be in between. Why? Because of resonance. That's the same reason. Okay, so I hope you understand. This will be the carbocation which will be formed. Right? Okay, good. Fine. Now we'll just go for it. I hope everybody understood. How do you decide which carbocation will be formed? That's the first step. If you make that wrong, entire thing is wrong. Right. Okay. Next. So I think I can rub this part. Right. 2 carbocations. Out of that, only 1 is going to get formed. Right. So let me write it in the top. So this H plus obviously has to attack this OH group only. Right. Okay. So what will happen then? You have pH, C, pH, OH2 plus C, pH, CH3 and OH. Right now what will happen? H2O leaves, you will form pH, C, pH, carbocation, C, pH, CH3 and OH. What is the next step? Rearrangement. Now I'll give you 10 seconds time, sketch the product. Now you have two different groups which can migrate. So fine, I'll not tell you, do 10 seconds. Okay, now hope you have sketched the product, right? So easily you can say that there is a lone pair here. Now this will come, make a bond. Obviously one of the bond has to break, either this or this bond has to break. Now that is going to depend upon the migratory power, isn't it? I told you that I gave you an order for migratory power. Obviously pH has more migratory power than CH3, so pH is the one which will come and attack the carbocation. Right? So if you would have gotten this as the product, then you are right. How many of you got this?
I got it.
I got it, sir.
Good. Anybody else? Good, good, good. Right. So that means you understood. Right. So first step is very simple. Form the more stable carbocation. And then when you're going for rearrangement, go for the rearrangement, go for the group which has more migratory power. That's it. Two things you have to keep in mind. Right? Fine. Now, one more example for penacol penaclone rearrangement. Okay, so this is what I have. H plus, go for it. And heating, obviously. So CHOH, CHOH, this is benzene ring with OMe, this is benzene ring with nitro group. Go by the mechanism. Please do not predict the product directly.
Sir,
Yeah.
can I tell the answer, sir?
Yeah. Okay.
Sir,
Yeah.
will the carbon atom with the NO2 thing get will the H plus attack the carbon atom with NO2 containing OH?
Okay. Fine. So you have to, for you to understand that, okay, this is NO2. Okay. Now tell me which is more stable.
NO2, sir.
Are you sure?
Yes,
How?
sir.
See,
Inductive effect, sir.
Sir, no, sir.
no. Here it is
more.
correct. First one is gonna be more stable. Now please understand, I have an electron, I have 2 electrons. This will come and this can go here. Right? But what happens in NO2? Maybe I'll write it here. Right? Now what happens in NO2? This bond will come here and this bond will break. This is like minus R. This is plus R effect. Right? Obviously,
Okay, sir.
electron donating groups will form more stable carbocation. So if I ask you, it is more stable, definitely this is more stable. Okay? Right?
Yes, sir.
Please be very careful. That's why I gave you this question. Even if you have different phenyl groups, aryl groups, then also you have to understand that it is going to be more stable. Okay, fine. So that question is answered.
Sir,
Yeah.
here also we should look into resonance, right?
Yes, definitely. Both will give resonance, right? But because of the presence of NO2 here, this is going to give me little of minus R also. But since you have an electron donating group, that means I'm going to have plus R. This carbocation, if it forms, is going to become more stable. Yes. Okay.
Yes, sir.
Right. Okay. So now, obviously, the H plus attacks this carbocation. Sorry, this oxygen atom only. Right. So I'll directly write the carbocation form. CH plus, I have an OMe, right? And this has a H and a OH and with an NO. Okay, now the migration has to happen. Now the competition is going to be between this, and as I told you, hydrogen is the one which will migrate, right? And how is it going to migrate? You will have a lone pair. This will come here, and this will come and attack here. So the products, if I have to sketch, there is OMe, there is CH2, already there's a CH, one more H, and C double bond O with a nitro group. Let me write it. Nitro group. This would have been the product. How many of you got this product? Nobody. Okay, fine. I don't know where you did the mistake. Maybe in this you would have done the mistake where you found the carbocation, or you would have forgotten that hydrogen atom is going to have more migratory power than this one. Hey, only 2 places you could have done the mistake, right? Please correct it wherever you done the mistake. Okay, so that is about pinacolone rearrangement. Okay, what is the time? Okay, I started by 10:10 only, so I still have 10 more minutes. Okay, now if I have vicinal diols, this is one of the reaction possible, right? Now there is one more reaction which is possible when I have vicinal diols. Okay, so I'll tell you what is that. Any questions, guys? How I got in the product? Everybody understood how the product is formed here?
Yes, sir.
Yes, sir.
Good, good. Right. Okay, so that is my oxidative cleavage by HiO4. HiO4 is called as periodic acid. Okay, HiO4 is called periodic acid, right? So this will happen. This is not only with vicinal diols. any two carbon atom attached to oxygen, any two adjacent carbon atom attached to oxygen atoms. Say this can be alcohol, this can be ketone, this can be an aldehyde and alcohol, this can be anything which has two carbon atoms which is attached to oxygen atoms, two adjacent carbon atoms attached to oxygen atoms, and this reaction will happen. Okay, right. For example, okay, actually I should try to write that. Okay, this should be the case. This oxygen can be in any form, alcohol, aldehydes, or ketones. Okay, say for example, now again the mechanism is going to be a little tricky. We are not going to look into the mechanism, but what I'm going to give you is a shortcut. Okay, so this is the shortcut you have to remember. So I have, for example, CH2OH, CH2OH. Now you see there's two adjacent carbon atom attached to a oxygen atom. What you're going to do is when I put HiO4, right, you will break this bond completely. The adjacent carbon-carbon bond you will break completely, and you put one OH this side, another OH this side. This is something like ozonolysis, but there only we will put oxygen only. Right, you'll break the C double bond, C, put double bond one, double bond to this side and that side. Exactly same, but you're going to break a single bond and put OH and OH on both sides. Right, now what will happen here? Can I say I will form 2 moles of CH2, OH and OH? Right, and I have already told you that 2 OH groups on the same carbon atom is unstable because of so much repulsions. Right, so what will happen?
Dehydration.
Good. So I have to remove a H2O. So you will form 2 moles of HCHO. Like you can just make HCHO, right? Correct. 2 moles of HCHO. Okay. So this will happen when I have HiO4, and if I have 2 carbon atoms consecutively having OH groups or any other form of oxygen, you will break that bond, put OH on the sides, on both sides, and get the product. Right, now the best example I can give you for HiO4, if I take glucose as an example, is it not? Now glucose, you see there are 6 carbon atoms continuously having all oxygen atoms. Right, so if I take them as an example, you will understand everything. Right, now this reaction can happen even if I have some lead oxide. No, what is that lead oxide? Oh my god, I forgot. Okay, please understand, either this or some lead oxide can also give this reaction. Okay, Pb3O4, if I don't want to give you something wrong, but it is definitely going to be some lead oxide. Okay, so that also is capable of giving the exact same thing. Right, okay, now let me take glucose as an example and let me write the reaction for this. Okay, pretty easy. Break the bond, put OH, that's it. Right, so I know glucose is going to look like this. 1, 2, 3, 4, 5, 6. Okay, so like anyways, I can just directly put HOH, OHH, HOH. Right, this is my glucose. Okay, now if I go for HiO4, now you see all the carbon atoms are having oxygens. Right, now blindly just break every bond and put OH on the sides. Right, say first, if I can use some other color, it will be little not looking nasty. Just give me a moment, guys. Okay, right, so I break this one, put OH. I think you're not able to see. Okay, so if I break OH, one is done. Another bond again. If I break OH, again break this bond. OH, break this bond. OH, break this bond. OH. Okay, I have done everything. Are you able to see, guys? Is it okay now? Right.
Yes, sir.
Right. So I've done the exact same thing what I've done. Break it, put OH. Right. Now I have to guess the product. Right. So you see this carbon, if I take first one, now I can take my black itself. Okay. Now if you take this carbon atom, I already have CHO, and I'm putting an OH to that. Right. So what is there? Basically double bond O, H is there. Right. Now what am I putting here? OH. This is the first product. Yes, no doubt this is formic acid. Okay, I had CHO and I added OH to this, it will become a formic acid. Okay, now you see 1, 2, 3, 4. All the 4 are going to give me the same product because all of them are CHOH, CHOH, and CHOH. Right. So if I can just look at one thing, I'm going to get 4 other products. Right. Say now this carbon atom, if you look, this carbon atom are already add a CHOH. Right. Now one OH is coming from the top, another OH is coming from the bottom because you see 2 sides the bonds are broken. Right. Okay. So one OH comes from the top. One OH comes from the top, the other OH comes from the bottom. One OH, another OH. Right. 2 itself is unstable. So definitely 3 is also unstable. What you have to do, just remove the water molecule. So what will you end up with? You will end up with HCOOH again. Right. If at all this will have become C double bond O, H, C double bond O, OH, again HCOOH. So 4 moles of this coming from this, and this. Right. Now last one coming to this carbon atom. This carbon atom had already had a CH2OH, and 1 more is coming from the cleavage. So you have 1 more, remove the H2O. So what will you end up with? You'll end up with HCHO. You'll end up with HCHO. So if I ask you, HiO4 is reacting with glucose, what are the products formed? You should tell that 5 moles of HCOOH and 1 mole of HCHO is getting formed. Okay, again I'll repeat from the first, starting with this, the first carbon atom that already had a C double bond O and a H. Now I'm putting 1 more OH, formic acid. Now this one, then 1, 2, 3, 4 carbon atoms are going to give me the same products. So this carbon atom had already had a H and a OH. Right. Now 1 OH coming from the top, 1 OH coming from the bottom. So there are 3 OH groups. Remove the water molecule, you will be ending up with formic acid again. And last, going to this carbon, it had a CH2OH. Right. Now 1 more is coming from the top. That's it. So you will form formaldehyde. Okay. So like this, I can go for oxidative cleavage with HiO4, or I think it's Pb3O4, but please check in your net. Right. So it's some lead oxide. Same reaction will happen. Okay. So I think everybody has understood. Right. So if there are maximum toughest question which can be asked with HiO4 is this only, nothing else. Okay. Right. So I think I'll stop with this for today, people. Okay. So we have completed all reactions with respect to alcohols, ethers, and phenols. I didn't complete. So phenols maybe next class I'll take. Okay. So phenols, not much reactions. You already know phenol OH group is going to be an ortho-para-directing group. So we are not going to see any Friedel graphs. The one main reaction I'm going to see is Reimer-Tiemann reaction. Okay. So that alone I'll see next class. And now obviously the mechanism is a little important. And then we'll go for aldehydes and ketones. Aldehydes and ketones, if I go, obviously the main reaction would be aldol condensation. Right. And there are few other name reactions which are not there in your NCRT that I'll teach you. Right. And in phenols, again, I have some name reactions, Fry's rearrangement. One more is there. What is it? Kleinsen rearrangement. like that something stuffs are there, right? So all those things we'll see. Very few reactions are left, okay, and we'll directly go for some problem solving. So I might take maybe one more or two more classes for teaching the theory part, right? And maybe one class is enough for entire problem solving. Okay, right? Fine, guys. Thank you so much. We'll meet again tomorrow, right?
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir.